Today I am here to present to you a lecture on optimization of concrete mix design using Taguchi and Topsis concepts. I will be covering this lecture into following heads: the problem statement, optimization, Taguchi design, Topsis approach. The validation has been done using paper, the results of which have been replicated to understand the Taguchi and Topsis method through a software called Minitab. Finally, two cases have been dealt with for optimization, that is geopolymer concrete and conventional M30 concrete. Then the geopolymer concrete, M30 concrete results, and finally the conclusion. The problem statement is optimization of mix design using Taguchi and Topsis concepts. Optimization. The Topsis and Taguchi method includes the idea of a multiple response robust design method to solve a multiple response optimization problem. The Topsis procedure is used to integrate all the determined factor and the values of the system into a single value that can be used for a single performance of a multiple variable optimization problem. The Taguchi design. Taguchi design, it aims at the minimizing the variance while keeping the mean on the target. The variance is reduced by optimizing the signal to noise ratio. Here signal are the parameters that can be controlled, whereas the noise are the parameters that can not be controlled. So, by reducing this we can reduce the variance. In the Taguchi design, we model the response into controllable factors and the noise factors. This leads to a robust process that's centered the target. Reduction in variation of the controllable factors, reducing the variance in the response, minimizing the variation in the uncontrollable factors, and hence help to sustain the process. The Taguchi design can be adopted when time and cost of experiment has to be lowered. There are a number of noise factors that have influence over the performance of the system, and there are different types of Taguchi designs which are a static response design in which a particular fixed value of output has to be achieved, and a dynamic response which aims at the performance of the system, and the optimum output response is a range within which it is efficient. The Taguchi designs following steps for optimization. The first one being the controls of variance, and second is to shift the mean to the target. The Taguchi design steps, there are 8 design steps in the Taguchi methodology. First is to identify the main function, the side effects and the failure modes. The second is to identify the noise factors and the conditions and the quality characteristics. The third step is to identify the objective function to be optimized. In the fourth step, it is to identify the control factors and their levels. Then is the selection of an orthogonal array from the array of matrix which have been designed by the Taguchi, and then conduct a matrix experiment which have been derived from the orthogonal array. Analysis of the data, predict the optimum levels and the performance, and finally perform the variation experiment and plan the future course of action. For this Taguchi design, we can adopt a software that is called the Minitab software for the, and above can be generated in the form of this software, wherein we have to decide the control factors and their levels, from which we get the derived orthogonal array, and according to that array matrix we conduct the experiments. To select the noise to signal ratio, there are 3 different aspects of this, whereas the output which we require should be, the higher value should be better, the nominal value should be better, or the lower value should be better of the outcome. This can be analyzed in the Minitab software. This can be done in the Minitab software by defining the noise to signal ratio and by analyzing the problem. Now the Topsis approach. In the Topsis approach is a simple and useful technique for ranking of the number of possibilities of the alternatives according to their closeness to the ideal solution. The Topsis procedure is based on the intuitive and simple idea, which is that the optimal ideal solution having the maximum number of benefits is obtained by selecting the best alternative, which is far from the most unsuitable alternative having minimum benefits. the ideal solution should have the rank close to 1, whereas the worst alternative should have rank or approaching 0. Mathematically, the application of software method involves the following steps. Firstly, establishing a decision matrix in which the columns are the criterias on which we have to select the ideal solution, and L, the rows, are the alternatives that we have for the same. Then calculation of normalized decision matrix, in which the normalized decision matrix is denoted, which represents the relative performance of the generated design alternative. Step 3 is the determination of the weighted decision matrix. So, not the all determination of the weighted decision matrix. In this, all the criteria will have different importance, and according to the importance which has the influence on the outcome, we will be giving them weights. In this step 4 is the identifying the positive and the negative ideal solution, and the positive ideal solution and the negative ideal solution are defined in according with the weighted decision matrix via the equation weighted decision matrix. Then the calculation of separation distance of each alternative from the ideal solution and the non-ideal solution, measuring the relative closeness of each location of the ideal solution. Then the calculation of the equivalent distance from the ideal best and the ideal worst solution. Then the ranking of preference of order and calculating the performance score, wherein the highest performance being number 1. Now, this was validated by an existing research of optimization of geopolymer mix. The strength oriented mix design of geopolymer concrete using Taguchi method was done by Shrimal Dave and Ankur Bhogpal, published in 2020, was validated using Minitab software. In the above study, L9 orthogonal array was selected, and the L9 array accommodated 4 variables with 3 levels each, and the total number of 9 trials. The governing factor of the mix design and the binder content, dosage of superplasticizer, NaSiO3 and NaOH ratio, and the molar content. Here we can see that the factors, the 4 factors with their 3 different levels have been shown. Here we have binder contents as 3, that is B1, B2, B3, which have different percentages of fly ash and GGBS. Factors and their levels in mixed design of L9 orthogonal array have been shown, which has been derived from the orthogonal array. That means there are 9 number of experiments that have to be conducted. Analysis of the workability results. The author had conducted the slump test, and the readings have been depicted in the bar chart here. Comparison of the results from the validation. We have the results from the paper that was published and the results obtained by validation which was done. Here we see that the results are similar in nature, and the results also show that the binder content has the most influence on the slump value of the concrete mix, followed by the dosage of plasticizers, and followed by the ratio of NaSiO3 and NaOH and the molarity. Response obtained in validation also reflects the same. Now, the analysis of the compressive strength results. Approximate values were taken from the paper, from the histogram. The results that are being shown are from the paper, and that has been validated, and the validation results are similar, which shows that the molarity of the geopolymer plays the most important role in the compressive strength of the concrete, followed by the binder content and followed by the dosage of plasticizer and the ratio of NaSiO3 to NaOH. The response was validated and similar results have been achieved. Thus, we see that the results have been validated and are almost matching, with the slight variation in the compressive strength, which is due to the values that are obtained from the chart are not accurate. Thus, the skills for using the software and the Taguchi method have been achieved, which have been incorporated in the 2 case studies that we have taken for optimization of mixed design. Now, the 2 cases that have been taken are the geopolymer concrete and the conventional M30 concrete. For geopolymer concrete, in case 1, geopolymer concrete mixed design was optimized to validate the influence of GGBS and fly ash on the workability and the compressive strength of the concrete, keeping other parameters like molarity, superplasticizer, ratio of Na to SiO3 to NaOH and OH constant. An L25 orthogonal array was selected to accommodate 2 variables with 5 levels of each, and 25 trials were conducted. The governing factor of the mixed design that were considered for optimization for different percentages of GGBS and fly ash have been shown. A complete mixed design combination for 25 trials have been shown here with different percentages of GGBS and fly ash. Now, analyzing the results of the experiment data was conducted for slump test, and the results are shown in the form of bar chart. Now, the results of the slump value shows that the 50% of fly ash and 30% of GGBS are the optimum values for achieving the slump values, for achieving a higher slump value. And in the response of signal to noise ratio results shows that GGBS plays important role as compared to fly ash in getting a better slump value. Thus, the result of this shows that GGBS influences the workability more as compared to the fly ash, and the percentage of GGBS increases, the workability will reduce. As the percentage of GGBS increases, the workability will reduce. Hence, the optimum value for GGBS is 30%, followed by 40, 50 and 60 percentages, and the optimum value for fly ash is 50% for achieving a best workability. Analysis of the compressive strength results from the experimental data we see in the form of the histogram. The results as shown here shows that 50% fly ash is the optimum value, and 30% of the fly ash and 30% of the GGBS are the optimum values for achieving the best compressive strength. In the signal to noise ratio results, we see that fly ash plays a more important part as compared to GGBS in terms of the compressive strength. Thus, the result shows that fly ash influences more towards the compressive strength as compared to GGBS, and the optimum value for fly ash is 50% and GGBS is 30%. Now, for M30 grade of concrete, in the conventional M30 grade of concrete mixed design, which was validated for workability and compressive strength again, based on the factors such as water to cement ratio, water content, cement, coarse aggregate, fine aggregate and admixtures and their levels, L27 orthogonal array was selected, and the governing factors for the M30 grade of concrete are as follows. There are 6 factors, each having 3 levels. Factors and level decides the L27 orthogonal array, which indicates that we have to conduct 27 trials. Now, we come to the analysis. After getting the results from the laboratory, the experimental results are shown in the bar chart. The results of the slump value shows that water to cement ratio of 0.3 is the optimum value for it, which plays the optimum value for slump results, and water to cement ratio is the most important factor which governs the slump value, followed by the admixture, the fine aggregate, the cement and finally the coarse aggregate. Here we can see that 0.43 water to cement ratio indicates the value which is the most optimum value towards the workability of the concrete. The admixture of 4.3 shows the optimum value for fine aggregate is 737.72 kgs, followed by 396.16 kgs of cement, 189 kgs of water and 1192 kgs of coarse aggregate. The analysis of the compressive strength from the experimental data, which has been shown as the bar chart. The results of the compressive strength shows that 0.43 water to cement ratio is optimum, and here we see that again water to cement ratio is the most important factor governing the compressive strength, followed by the fine aggregate, the admixture, cement, and finally the coarse aggregate. Now we can say that the higher water to cement ratio is better for compressive strength, and second most influencing parameter is the fine aggregate. Now once we have applied the Taguchi method and found out the optimum values and the most influencing factors of these parameters, now come to the Topsis approach for M30 of conventional concrete. In this, the alternatives according to their distance from the ideal solution, negative solution and positive solution, we find out the best alternative. The ideal solution is identified with a hypothetical alternative that the best value for all considered criteria, whereas the negative solution is the identified with the hypothetical alternative that the worst criteria value. Here we see that the criteria as water, cement admixture, the slump value and the compressive strength, and the type of criteria tells us whether we want a higher value for it or a lower value for it. The negative indicates that we should have a lower water value. Again, cement we should negative value shows that the minimum value should be the best, and for slump and compressive strength, the higher the values, the better is the solution. And accordingly, with the importance of different parameters, we have given them weights. Here we can see that the slump value and the concrete compressive strength have the higher values, higher weights, higher importance as compared to the other factors, and accordingly weights have been assigned to them. From here a decision matrix is made, which have been taken from the Minitab software, in which we had applied the Taguchi method, and we have the ranks of the different 27 trials that we had conducted, which we had found out from the Taguchi. And then after the Topsis approach, we are finally in a decision, we have achieved a final value that the trial 15 is the best out of the all 27 experiments, which satisfy the optimum values that we had analyzed from the Taguchi method. Now the results, the mixed proportion of L trial 15 are as mentioned in here for different parameters, and the results that we have achieved in the compressive strength, the 3-day expected value of the compressive strength was to be 15.3 newtons per meter square, which is the 40% of target strength, and in 3 days the results that we have achieved is higher than the value which was expected. Here we have obtained from the laboratory indicates that the compressive strength achieved is higher than the expected value, and hence it is validated that mixed proportion will give the desired strength, keeping the ingredients at the optimum level. With this, I would like to conclude that the concrete mix design may consist of conflicting factors, and a systematic methodology will have to be applied in the optimum mix design and to analyze the most effective factor under the constraint. For this reason, multi-response Taguchi method was used to investigate the conflicting factors and their levels, and finally getting the optimum value for each criteria. And after that, the Topsis method was used to transform this multi-response into a single response problem. The two cases of mixed proportion were identified to be optimized and conducted as under. In geopolymer concrete, the GGBS influences more towards the workability, whereas in the compressive strength, the fly ash contributes more, keeping other parameters as constants. In the M30 conventional concrete, the trial 15 was the optimized mix design, and which satisfies the properties of M30 grade of concrete after the tests were conducted. and the results were obtained. The result shows that the proposed methodology is effective in solving the mixture proportions for optimized design, and by using this robust method of Taguchi, we can find out the optimum value of the different ingredients. Jai Hind.